let's talk about instantaneous rate of change, average rate of change, and secant lines and tangent lines, all in the context of a particular problem where we have an object following a path. So we're working in the world right now with mathematical models, and I've got a model for how the object is traveling, and we're thinking of this function y as being the height of an object, say, at some particular time. And we can just plug in a time, and we get back the height that the object was at. Right? So we have position data about the object. Right? This right here is position data. And given position, it seems like it's really reasonable to request, well, we know where something was, how fast was it going when it was there? And that's the question of instantaneous velocity. So we're going to focus our attention on a particular point in time, t equals 1, and we're going to estimate the instantaneous velocity as the result of a sequence of calculations of average velocities. So the method is going to be use average We're going to use average velocities. Okay. So when we're estimating values for limits, we have that numerical tool in our toolbox. And we're going to choose a sequence of values that converges to the value that we want the limit at. So we want a limit at t equals 1. So we want a limit at t equals 1. So we're going to choose a sequence of values that lead to t equals 1. So let's say do 1.5, 1.1, 1.01, and then maybe more terms if we can, if we need them, and eventually we have the hard limit L that we're going to want. So that's when t equals 1. Okay, so these are my t values. And what I'd like you to notice is that each of these t values is some distance from the point that we're really interested in. So we're really interested in this one, and we could express the distance each of these is from this one by, say, writing like delta t. So I'm going to put the delta t right there, and that's going to be the distance that this time is from this one right here. So 1.5 minus 1 is 0.5, and I like putting zeros before because otherwise the dot gets lost, I feel like. This one is delta is 0.1, delta is 0.01, and eventually we get down to like 0, but I'm not going to write it because we can't actually compute anything down at that point. Okay. Ultimately we want to compute the slopes of secant lines at these various points because slopes are average velocities. Slopes are velocities. So I'm going to draw a little picture for you, and you should follow along. So let's draw a picture of this curve, 60t minus t squared. It's a downward opening parabola, and it's going to look something like that. It's a downward opening parabola, not to scale. That's our t-axis. So the height of this function is the height of an object that's traveling along this path. So then this curve right here is y of t. T equals 1 is down here. And the thing that we're trying to estimate about this is the slope of the tangent line right here. So that tangent line, which just barely touches the function, just barely touches the curve, touches at exactly 1 point. And we only have 1 point on the curve, but we need 2 points to write a position, to write a line, so we need a second line. So we want the slope of this. So the slope of this line is the instantaneous velocity. But we can't get it, so we're going to settle for computing secant lines. So here's a secant line. Oh. There's a secant line. And we're going to turn the secant line into the tangent line by doing a limiting process. And the slope of the secant line is the average velocity. Okay. So I've got a sequence of times that converges to the time we're really interested in. And those are going to live down here. So I'm, say, going to have this time right here. Say 1.5. And the distance between these two is my delta t is 0.5 for this particular one. So I have point right there, and I have a second point that lives on the secant line that's determined by this time, which came from this table. And we're going to turn this time into 1 by doing a limiting process. The coordinates of this point are 1.5, the function is the thing that governs the second coordinate of all of these points. So we're going to take this time and plug it into this function to get the second coordinate. So I'll go ahead and do that on my handy dandy calculator. I'm going to go 60 times 1.5 minus 16 times 1.5 squared, 54. Okay, the other one right here is 1. And then in order to get its second coordinate, we've got to take the value 1 and plug it into this function up here. So it's going to be 60 times 1. I know how to do that. That's just 60. Minus 16 times 1 squared. So 60 minus 16 is 44. Okay. So I have a line. I have 2 points on it. And I want the slope of this line. I have 1.44 and 1.5, 54. So we're going to invoke our friend slope. The slope formula, rise over run. So delta y over delta t. And the slope is then 54 minus 44 divided by 1.5 minus 1.0. Okay, rise over run. The top of 54 minus 44 is 10. 1.5 minus 1 is 0.5. So the slope then is 10 over 0.5, which is 20. Okay, so we have the first term in our sequence of slopes that we're going to compute. And as we get closer and closer to 1, these slopes are going to get closer and closer to the slope of this tangent line. We just don't know what it is yet. Is it 20? It seems doubtful because 0.5 is pretty far away from 0. Like this 1.5 it seems really far away from 1. Like in the scale of things, like think how many zeros you could put right here. So 0.5 is pretty far away. But hey, okay. So let's do another point. Let's do this next one right here. So let me erase the relevant parts in this thing. So that base point, that 1.44, sorry, the 1,44, it's not changing. That one's fixed for this computation. So we'll take the 1.1. That value is now 0.1. 1.1, comma. We need its function value. The function value is determined by the function. So we'll go 60 times 1.1 minus 16 times 1.1 squared, 46.64. So 1.1, 46.64. Do the slope. Is going to be 46.64 minus 44 divided by 1.1 minus 1.0. All right, so this is going to be 2.64 divided by 0.1 is 26.4. So it moved a fair amount, right? It moved a fair amount. Let's see what happens as we get even closer to t equals 1. 1.01. So we'll erase those. That one's going to change. That one's going to change. That one's going to change. Okay. So 1.01, 1.01. So our function value, we're going to take that t value, and we're going to feed it into the placeholder for the value that wants to be eaten. We're going to go 60 times 1.01 minus 16 times 1.01 squared, 44.2784. So I'm going to do that in the slope formula again. 44.2784, 1.01. Compute the difference between those two things. So my numerator in my slope computation over here is 0.2784 divided by 0.01 is equal to 27.84. I think I just went off the screen. Yep. So I'll just wipe that, and we'll call it 27.84. So it's like 20, 26.4, 27.84. Do you think you know what's going to go to if we keep doing this? My guess is 28, but I'm feeling a little dodgy on, I'm feeling a little iffy on whether that's really 28. So let's do another 0. Let's do another term in the sequence. Let's go 1.001, 0.001. I'm going to kind of not bother to rewrite some stuff in some places. So let's just go ahead and evaluate our function at 1.001. I know I'm going to need more space because it's going to be a longer number. Okay. So 60 times 1.001 minus 16 times 1.001 squared, 44.027984, 1.001. So the difference between these two numbers is getting really small, right? Between the two function values, because these 2 points are getting really close together. We've like slid this point over pretty far, and we're like really close to the other one. So they're like really close. So that's 0.02794 divided by 0.001. That's our estimate on the slope. This is just like multiplying by 1,000. Move that decimal place over 3 places. Boop, boop, boop. 27.984. And it's getting pretty close to 28. So at this point, I'm willing to conjecture that if we were to keep doing that forever, that the slope of the tangent line is 28. Slope of the tangent line is 28. So our goal was to estimate the instantaneous velocity when t is 1. We just computed the slope of the tangent line when t is 1, but those are the exact same thing. The slope of the tangent line, that line that just kisses your function at one point, that slope is the same as the instantaneous velocity of something traveling that path. And to me, that's just absolutely incredible. I love that fact, and I think that it's really, really amazing. So one thing I want you to pay attention to, if you're doing something like that, is that the numerator, when you're doing the slope calculation, the numerator is going to 0. The denominator here is going to 0. If these aren't both going to 0, then like something's weird in your calculation, and you should check your work. That then suggests that this thing right here is going to turn into like something that looks like 0 over 0, which is really why we need the algebraic rules for doing limits, because we really want to deal with like how do we get away from this 0 over 0. So as we move further into our discussion of limits and rates of change in Chapter 2, we'll find tactics for dealing with what happens when we have 0 over zeros. Cancel a common factor. So again, to sum up, we started with a function, and we want to estimate the instantaneous velocity at some particular time. We chose a sequence of times that leads to the time that we're interested in, and we computed slopes of secant lines. We computed average velocities. These are all average velocities. And by getting arbitrarily close, by getting closer and closer and closer to t equals 1, we can make these numbers here arbitrarily close to the value that they're converging to. And so I'd encourage you, if you want to see the next step here, go ahead and throw another 0 in here, and you'll see that this value, this 27.984, gets even closer to 28. And if you just chose some small distance, you said you wanted this number to be within this number, some small number of this number, all you have to do is make this number sufficiently close to 1, and that's why it's a limit. So thanks for watching. I hope my first ever learning glass / lightboard video was enjoyable / usable / helpful. And I will hope to see you sometime later. Thank you. Bye.